Last time after we had our lecture, suddenly a thought came to me, and I'm just going to share it. It's got nothing to do with, as such, this particular course. But what I want you to do is, whenever you look at something, look at a process, ask whether there is a potential for applying it somewhere else or for some other purpose. So, what basically I was doing was I looked at, you have seen this, this is the Hall Herold process. And what are we making? We are converting alumina to aluminium. At the same time, one of the things which is interesting to consider is that in the future, one of the big problems of this will be that it requires a lot of energy. And so at some point, that energy is going to come from some other source. Maybe nuclear energy, maybe nuclear fusion, maybe solar thermal energy is possible. So there should be a concern that you should have around where is this energy going to come from, and not just for this. Across all of chemical technology, many of the processes are energy intensive, and where will this come from, and what role does a chemical engineer have in this entire debate on net zero, which people are talking about? Where do we all fit in? So I think that that's important for you to know. And second is that if, for example, one is talking about solar energy, and not just solar, but in many other cases, actually, what we have to also look at is this whole business of being able to store energy, because you may or may not be able to utilize all the energy only during when it is being generated. Energy has to be stored. In a thermal power plant, of course, there's no issue because you are constantly burning coal and generating power. But if you are working with, say, solar energy, you may be able to reach very high temperatures, carry out chemical processes. All that is fine, but one will have to look at storage. So I was actually thinking, you did not respond to it, but you can think about it. Maybe it's all absurd, what I'm thinking. But I was actually thinking that because this aluminium to alumina process is highly exothermic. So you can see minus 1596 kilojoule per mole. That's really the amount of heat that is being liberated, the delta H for this process. So I was actually thinking that could it be that maybe at some future date, maybe what one can do is if we can achieve these kinds of high temperatures by solar thermal energy, and you can easily reach temperatures of 1,000 degree centigrade. And so it's possible that, or I mean, that combined with the fact, or it could be that you have solar photovoltaics, and from photovoltaic you run your Hall Herold process during the day and generate this aluminium. And maybe at night, what one could do is that the aluminium plus the because it will all be in molten state plus the cryolite that can be pumped into another reactor, and you could pass oxygen. Perhaps that will convert the aluminium back to alumina and generate huge amounts of heat. And so one might be able to actually use it as a means of storage. Now, why I was attracted to this is because the alumina which will form, you see, if it was formed as a solid, there would be a problem. But because alumina dissolves in cryolite at those temperatures, so I will be able to have a a molten mass, a pumpable molten mass. And then once it become that, during the day, put it back into your Hall Herold cell, and again reform aluminium. Normally there would be a problem, because moment you take aluminium and oxidize it to alumina, it may form an insulating coating, and that might prevent the further oxidation. That's always a problem with aluminium. But one is that the aluminium would be in a molten form. Secondly, because of the presence of the cryolite will dissolve away the alumina which is formed. So I will be able to generate a clean surface for oxidation. This is just a wild thought, but the reason why I'm trying to share it is that always think about whatever you're learning, and that where can I possibly apply it additionally. So just keep this in mind, and later on, when we cover ammonia, you'll find something similar, which we'll be discussing. Yeah. Now, what we'll do is discuss air. Air means separation of air. Air and water are two very, very important utilities which one requires. And many times we take air for granted, but air is really not to be taken for granted. It's very important. So let us try and see what is the kind of things that you have in air. It's mainly, as you know, that roughly about 4/5 is nitrogen and 1 part is oxygen. But air also has a fair amount of argon, something like 1%. And argon is a very important gas in its own right. There are, of course, small amounts of other things also. This one is steadily going up. The carbon dioxide in the atmosphere. Today, as you know, it's about close to about 412 ppm in volume by volume, and it might go up further. So we have actually already crossed these limits. But they may actually, it's possible that later on you may actually want to recover carbon dioxide from the atmosphere. All this net zero is all about that if you are going to produce carbon dioxide, you must also find a way of taking it out from that, either through planting more trees and mopping up more CO2, which is frankly the easiest thing to do, okay? Or there could be certain technologies with which you can try and extract carbon dioxide from the atmosphere, and that is really to try and contain the temperature to 1.5 degrees centigrade rise, that what everybody is talking about, all right? So carbon dioxide actually from the atmosphere could become a feedstock in the future. But right now we have to look at it more for its nuisance value, not just in terms of the heating up of the planet, but also that it can interfere with the separation of nitrogen, oxygen, and argon. So you need to look at that. We'll of course go to some of these details a bit later, but you can see, I mean, air is not so simple. By the way, I mean, this is air as we knew it maybe before the Industrial Revolution. That's what air was. Air was like this. Okay? Today, air is not that. Today, there will be a lot of haze. You take your photographs and you'll be able to figure out that many times the images look hazy. There's a lot of particulate matter in the atmosphere because of burning of fuel. There's a lot of unburnt hydrocarbon. Then you have got SOx, NOx. So air today is far more complex than what it was when it was really pristine air.
So one more contribution to the hydrocarbons can be the vaporization that takes place at the pumps. Like for even a minute amount of time that we keep our tanks open to fill the petrol or gasoline or whatever.
Yeah. I mean, in fact, vaporization, it's a very good point. Vaporization is a important point, but the biggest contributor to hydrocarbons, one is of course the fact that combustion is not 100% complete, and the second, and which you will find a lot of times, you'll see these diesel fumes and all, and if the engine is not properly tuned, you see the amount of the smoke and all that comes out. A lot of unburnt hydrocarbon. But another is actually cattle. I don't know if you know, but cattle
Yes,
are
sir.
responsible for huge amount of methane generation, and that methane really escapes. And in fact, there's a lot of work in trying to reduce the methane emission from cattle. I don't want to go into all those aspects, but just to basically say that there are complexities today which did not exist 300, 400 years back, and air is much more complex than what is shown in this chart. Now, the other thing is that if you look at air, and especially from a chemical engineer's point of view and in manufacturing, one doesn't realize the amount of air that we actually consume. You've gone through sulfuric acid, you you require about 2.8 tons of air per ton of sulfuric acid. 1 ton of coal that we burn takes about 10 to 11 tons of air. The reason is because you've got it's only 20% which is oxygen. So you're talking about something like 2 tons, and that will be about it. Now, 1 ton of coal will require about 2 tons of oxygen because you have CO2, right? And so I mean, and their atomic weights are comparable. Oxygen is 16 and carbon is 12. So you can quickly do a mental sum, and you'll be able to figure out that these figures are all reliable. So it's a lot of oxygen, and in terms of air, and that's not all. We don't take into account the fact that, let's say, we are 1.3 billion people, okay, or maybe 1.4 now. Can you imagine everybody consuming food and breathing in oxygen and breathing out carbon dioxide? How much carbon dioxide is actually going into the atmosphere from us? And for each human being, just count the number of other animals that exist in the planet, and they are all emitting CO2. So it's not just uh, chemicals manufactured, but us. You can actually look at, let's say, calorific value of food, and I mean, obviously it will be an approximation, but nonetheless you'll get an idea within about maybe plus minus 30% that how much of oxygen would have got depleted, and how much of carbon dioxide would have been produced from us. So this is again important. And by the way, if you think that air looks so vast that no, I mean these things cannot make a difference, it's not true. There has been a decline in the atmospheric oxygen level, and it is comparable to the amount of fossil fuel emissions of CO2. And of course, fossil fuel, because even our food, etc., when you are making fertilizers, etc., to grow our food, obviously there is an indirect footprint of fossil fuel for that. So there is a relationship. And so oxygen is coming down in the air because of all this massive consumption of oxygen from the atmosphere, which we don't realize. So bear this in mind also. Now, what of course we will be looking at particularly over the next maybe couple of lectures is the separation of air into oxygen, nitrogen, and argon. Why? Because many applications actually require pure oxygen. So you'll have to look at, and there's a lot of requirement of pure nitrogen. There's a lot of requirement of pure oxygen. But then you can imagine that if you've got a lot of unburnt hydrocarbon in the atmosphere, and if something happens, like let's say if I produce pure oxygen, liquid oxygen, and a lot of the hydrocarbon, suppose it dissolves in that oxygen, the hydrocarbon in the atmosphere, that, I mean, there could be an explosion. Yeah? There's a lot of things that you need to look at, and I'm just trying to point out a few things which are rather obvious. And then, many times we know that if you are using air and if there are impurities like SOx and NOx, which can make the your medium where you're carrying out a reaction or whatever acidic, that there could be problems. So again, I mean, they have to be removed. Okay, and then we also know that there are many applications where you actually require dry air. It's not just wet air. So the moisture content in air is also very, very critical for many applications. These are all the things that one needs to keep in mind. Okay. Now, let us look at oxygen first. We know, I mean, oxygen has a lot of applications. By the way, there was a time when people actually were, at the time that they were discovering oxygen, and the great work of Lavoisier, and they actually referred, like when oxygen was being used for combustion, and finally all the oxygen in the air got consumed, and they didn't know, and they would call it burnt air. I mean, that is, it's exhausted of its vitality, and it's burnt air. I mean, that was the term that was used after combustion. Where would one need pure oxygen? Which are the applications?
Sir, in steel plants.
Steel plants, okay.
So oxygen cylinders.
There you go. For, you mean
So
for
hospitals,
hospitals and all? Huh?
Yes, sir. Yes,
hospitals,
sir.
Oxygen cylinders
So for underwater divers as well.
for hospitals, underwater divers. Very good. Anything else?
So contact process.
Contact process, you use air.
So but
You don't use pure oxygen.
so but it depends upon the pressure of oxygen, right? With
Yeah,
V2O5.
yeah.
So
I know. Of course, you could have used pure oxygen, but I'm just saying it's not so critical, and nobody uses pure oxygen in the contact process. You could, it's just an added cost.
okay, sir.
nitric acid plants.
Nitric acid of plant also, you will use air. We use oxygen, but we use it in a mixed state. There are certain applications,
Sir, in
applications
oxyacetylene
where,
torches.
like when you said steel plants, what did you mean?
Sir, cutting of steel using oxyacetylene torches.
Yes, I think that, so you can generalize, okay, not just steel plants. I think it's better to say oxyacetylene flame.
Yes, sir.
It's very interesting that it was in the later part of the 19th century that acetylene was first made from calcium carbide by Henry Moissan. Then, of course, people discovered that acetylene along with oxygen can give you temperatures which are extremely high, and that actually gave birth to many of these metallurgical industries, processes. So it was that important, and so there was a huge interest in getting pure oxygen. The nitrogen was less important in the early stages. Although let me tell you that the people who actually invented this process, Linde and all, they were initially, I mean, not so much Linde, but there was a Britisher who also played a very important role. And they were actually looking at refrigeration, and they were looking at alternatives to dry ice and things like that. And so they were very interesting things which actually triggered this entire interest in what later on became the Linde process. Any other application other than this?
So rocket
Sir,
fuel.
Yes, yes, rocket fuel, propellants.
Sir,
Very
fuel
nice.
cells.
Fuel cell. Now, fuel cell also you could actually use air also, right, in a fuel cell. Although, of course, it would be beneficial to use oxygen, but it's not mandatory to use pure oxygen. Okay? You could use air, but these would be more like things that you will require oxygen for. Rocket fuel, oxyacetylene flame in the hospital. I mean, so many people were having problems, right, during COVID, and the biggest problem was oxygen. In fact, it's also interesting if you look at this article, this from 2020, and when there was a massive shortage of oxygen because it was all getting diverted for into hospitals and personal homes for treatment of COVID patients. Many of the industries actually came to a grinding halt, and it was then that it became evident that so many industrial units actually required oxygen, and you can see industrial units gasped as oxygen diverted for medical use. I mean, obviously, oxygen has a very important role, even pure oxygen, in industry. Now, let's also look at nitrogen. Where do you require nitrogen?
Sir, for packaging food.
Packaging.
Sir,
Huh?
for fertilizers.
Wait. Let's put down. I'll later on take it. What did you say? Packaging.
Sir, to preserve the food, they fill nitrogen in the packet.
In fact, it's quite common today. You look at your Lay's potato chips and all, and they look like a balloon. And many times, they just put in some nitrogen, okay, and pack it with that, just so that the potato chips and all don't get rancid. So yes, packaging is one. Anything else?
Dyes. Making dyes.
Making dyes,
Yes, sir.
but pure nitrogen. Where?
No, sir. No, sir. In compound.
I'm talking about pure nitrogen means N2.
Oh, so
I'm
sorry,
not
sir.
talking about compounds that contain nitrogen.
So nitrogen fixation.
Probably one of the biggest, nitrogen fixation. You cannot have oxygen there.
Sir, to provide inert at atmosphere for metallurgical operations.
Yes, inert atmosphere. That's what you're trying to say?
Yes, sir.
Right. Great. What else?
In vehicle tires.
Vehicle tires. Yeah, I mean, you don't want any kind of degradation of the polymer. Not the majority of vehicles. They just use air.
So as a refrigerant or coolant, liquid nitrogen.
Brilliant. As refrigerant. coolant. Brilliant. I think you have covered some very nice points. What I'll do is maybe take you through a few more. And some of them which you may not necessarily think of. Like, for example, you have mentioned cryopreservation, the cryo under cold conditions. Today, in fact, there are people who are preserving their bodies after death so that, in case the technology advances 50 years from now and they can be suddenly brought back to life, there are people who are actually not burning their bodies or burying, they're cryopreserving, okay, in the hope that some miracle might happen in the future and they might come alive. The cold part of nitrogen is being used for cryotherapy. There are things that people do, especially for skin treatment, etc. Rapid freezing. If you look at all these fish and things today, I mean, there's glass freezing. I mean, they are almost frozen instantaneously, so that there is absolutely no putrefaction that occurs. And sometimes you don't realize, but there are very interesting things like, tell me one thing. Suppose I give you a rubber tube and I say that you make it into a powder. How would you do it? Or some other polymer like polyethylene tube or milk pouch, and I say I want to crush it up and make a powder out of it. How would I do it?
So we will use a grinder.
Just take that polymer and grind.
So freeze it and grind, sir.
Yes, correct. And why freeze it? Because you want to go below the glass transition temperature. Because then it will be like a solid, otherwise a rubbery material is very difficult to grind. This is a very important area. People don't realize many of the ion exchange resins, which are in a very fine powder form, those resins have to be actually comminuted. Cryocomminution is a very interesting process. Then we don't realize all this talk about trains which will run with magnetic levitation. Today, the temperature that you are able to get superconductivity at, earlier it was liquid helium temperature, but today there are materials which are superconducting at liquid nitrogen temperature. Nobody really has been able to make anything superconducting at room temperature, although there have been many such false claims, but invariably they have been proved wrong. But the last big breakthrough was really bringing it to the liquid nitrogen temperature, which was itself a huge finding. In fact, we know also that, for example, signal to noise ratio. One of the best ways to improve the signal to noise ratio is really to operate at lower temperatures. And so when you have extremely sensitive detectors, like some of the CCD cameras which are used in astronomy or in doing X-ray crystallography, these are all cooled detectors. Many times sometimes you have to cool it to liquid helium temperature. So there are huge applications, but you also need to be cautious. So like, for example, both for liquid oxygen and nitrogen, it is not just their applications at room temperature, but the fact that in making these oxygen and nitrogen, at least by one of the technologies, it involves liquefaction, and therefore I am able to go to very low temperatures, and that has opened up huge applications of something being cold. And then imagine transportation. When you have got liquid nitrogen, liquid oxygen, what a massive reduction in the volume for transportation. So it's very, very important. But then also be careful. Sometimes what can happen is people don't realize you can get asphyxiated, you can have frost bites. You'll find that oxygen has a higher boiling point than nitrogen. When I'm trying to make liquid nitrogen, if you're not careful, the oxygen will also get into this thing, and there could be violent oxidation even when liquid nitrogen is exposed to something which serves as a fuel. So there are many things that you need to be careful about. Look at this air business in a broader way, and then it gets quite interesting. Let me ask you, what would be some of the ways of separating oxygen and nitrogen?
So fractional distillation of air.
Very good. Which means that first you have to liquefy air, right?
Yes, sir.
So we are talking about then liquefaction of air followed by fractional distillation, right?
Yes, sir.
What else? Any other way of separating?
So can we use any magnetic principles?
I think what you have in mind is that oxygen is paramagnetic.
Yes, sir.
That's what you're trying to say. Drawing on paramagnetism of O2. Anything else?
So passing through pyrogalol solution so that oxygen is...
Brilliant. Passing through. Okay. Which means you're talking about selective dissolution. Is that what you're talking about?
Yes, sir.
Okay, great. Anything else?
Sir, is there any way so that only oxygen reacts in a chemical reaction and then we can recover it later?
All combustion processes.
And then we can recover it later.
If we use mercury in this particular process, then it will form HgO, and then if we reheat it, then oxygen will be released from that compound.
Yeah, so there would be, what you're saying is that chemical processes to make oxides and then release oxygen from those, right?
Yes.
That's what you mean, isn't it? Like HgO. That's what you're trying to say. Correct?
Yes, sir.
I would say 4 and 5 have some commonality. No, except that 4 would be useful for nitrogen and 5 would be useful for oxygen.
So using gas chromatography?
Gas chromatography, very good. Actually, you can separate nitrogen and oxygen with adsorbents. So, gas chromatography, I will say generalize to principle of adsorption. Try to always give the more generalized principle. Anything else? I think you've given some very good answers, but I was just hoping maybe 1 or 2 more. Okay, now let us, for example, look at this. Okay, now this particular thing had more, its focus was more on how to get pure oxygen, not so much on how to get pure nitrogen. But still, it gives you some idea, and actually you have covered most of them. Like adsorption, you said gas chromatography. Well, it's adsorption. Maybe the adsorption is done in a different way, but you have talked about chemical. Yes, chemical. I mean, one is that chemical could be that I'm talking about solubility, or I'm talking about actually chemically reacting and then recovering something. There would be differences in the chemical behaviors in terms of solubility, etc. Cryogenic, you have talked about liquefaction and fractional distillation. Membrane, there is a difference in the size of nitrogen and oxygen, N2 and O2. And so their permeation through membranes tends to vary. You cannot maybe get very pure oxygen or so. but it's not many times required. I mean, maybe if I get, say, from 20% oxygen, if I can make it 50% oxygen, maybe the doctor can keep somebody going for a longer period of time. You don't need always 100% oxygen. Or if you want to do an improved combustion, maybe by taking enriched air, I can improve the efficiency of combustion. ITM, that is, you'll find these are, there's a method whereby you're not taking advantage of the paramagnetism of the oxygen, but what you are taking advantage of is the fact that it is paramagnetic because it's in the antibonding orbital. There are 2 electrons there, and because it's in the antibonding orbital, if you kick off an electron from O2, then the bond strength improves because you've lost one antibonding electron. So you can actually form O2 plus. So you have made one ionic, and nitrogen, you cannot do that, and so you might be able to transport as an ionic substance. So you can see that there are very interesting ways of doing this. You talked about adsorption. That is great. I mean, you talked about gas chromatography. Okay, and it's true. You can separate oxygen and nitrogen by GC. Now, what is more commonly used are zeolites, especially some of the zeolites like zeolite A has been used. In fact, my colleagues in the previous place where I was, they had developed this sort of a unit, long time back, 1999, 2000, and these units are quite popular today, okay, all over. When you talk about O2 and N2, while of course oxygen is more reactive than N2, but that's really not the basis of adsorption. It's a bit different. And what it is that what's the dipole moment of nitrogen and oxygen?
So 0.
0. Perfect. So they don't have any permanent dipole moment, but there is a polarizability of these molecules, O2 and N2. If you were to put them in an electric field, it would induce a dipole. And that's what is meant by polarizability of a molecule, that the extent to which the dipole is induced, the magnitude of the dipole moment divided by the electric field. This is what again creates the dispersion forces. Some of the van der Waals interactions arise from this kind of induced dipoles, from polarizability. And the properties of nitrogen and oxygen in that sense are quite different. Suppose I've got a neutral molecule, but now suppose I put in let's say a charge in the vicinity of the molecule, it will induce a distortion of the electron cloud. And so the electrons would tend to move towards this. Or if you have got a dipole, then this is the way it will happen. So I have basically induced a dipole. And now what happens is that I've induced a dipole, and I'm in a way forcing the molecule to interact with me because of the induced change that I have brought about. And that's what happens in like, let's say in a zeolite, in these cavities. What you have is that firstly, it is known that you have a very non-uniform electric field. You know that there are mobile cations in a zeolite, and plus of course you've got stationary charges which are negative. And so what happens is that it's been found that the interaction of O2 and N2 with zeolites tends to be very different. Which would you expect to interact more?
Sir, N2.
Wonderful. I can write that the induced moment, dipole moment, is basically equal to the polarizability multiplied by the electric field. So if you were to multiply, then you'll end up with Coulomb meter, which is basically the unit of dipole. So that's the polarizability unit. Now, polarizability is related to also what is known as the quadrupole moment. So all these molecules, like which are otherwise zero dipole moment, actually can have an induced dipole moment. And what I'm talking about is what is known as the quadrupole moment. Quadrupole moment is, like I can have, say, two molecules which are anti-parallel to each other, not fully aligned. Maybe they would have a phase shift in the way they are interacting with one another. So all of those things can give you what is known as a quadrupolar moment. It's better to understand it through, let's say, a magnetic pole. If I have a single magnet, I can have a north pole and a south pole. Now I can have an arrangement, where I have a north pole and a south pole. So this will be interacting. Okay, I have a south and south; they will be repelling. And again, I have a north and south here. So I'll have the lines of force will go like this, like this, like this, like this, like this. These kinds of quadrupolar magnets, for example, are used for very tight focusing of charges like electrons in high resolution microscopes, etc. The sum and substance is that the quadrupolar moment of nitrogen is about 6 times higher than the value for oxygen, and therefore nitrogen interacts much more strongly with a non-uniform electric field, as for example it exists in zeolite. To the extent, the interaction energy, if you were to do a heat of adsorption measurement, you would find that the value would be about close to about 10 kilojoule per mole. It's a fairly good interaction. Is getting into the domain of hydrogen bonding kind of interactions. Maybe not that strong, but nonetheless quite strong. So effectively, what you do is that you have these beds of zeolite. First, you make sure that your air is filtered to remove all the impurities like SOx, NOx, hydrocarbons, etc. Because otherwise, those will go and spoil the catalyst. Your bed, these will interact with your zeolite, and it will lead to a loss of stability. So remove those, and then you pass it through this, okay, with the help of air blowers. So you are actually creating a positive pressure, not a very high positive pressure, but a marginal positive pressure, and your nitrogen is getting absorbed. Some amount of oxygen will also get absorbed, because after all, oxygen also has a quadrupolar moment, 6 times lower than nitrogen, but it's there. So some oxygen will also absorb, but typically what will happen is that all the nitrogen will get absorbed, or most of it. So what will happen is that I'll end up getting pure oxygen coming out. So I can actually get pure oxygen, reasonably pure. When I say pure, means maybe about 90-95% pure oxygen you can get through these systems. By the way, today, these are actually used in many of these, even in the Linde process, etc. There is a pre-treatment many times which is done where you use such things to effect initial separation. And then once your bed has got saturated with nitrogen, then what you do is a pressure swing. You pull a vacuum. So now the nitrogen will get released, because these are very weak interactions. So just by changing the pressure, high pressure to low pressure, I can make it absorb, or I can make it dissolve. So the nitrogen comes out, and it will be treated as a waste stream, because there will be some amount of oxygen there also. So you chuck it away. You don't use it, so you let it out into the atmosphere. That's how you regenerate your bed. So you may have some beds which are always in the making mode, where you're actually recovering oxygen, and then some will be in the regeneration mode, where you're regenerating it, and that way you can get a continuous process. Is it clear, the process of adsorption for separation of oxygen?
Clear, sir.
Okay. One more thing that I should mention, when I'm telling you about all this, is that it's also important that in these kinds of units, you start getting your product, like your oxygen, right away. You don't really have to wait. Like if you're putting someone in a machine, you have to supply the oxygen quickly for medical use and things like that. So these units are very good from that point of view, that straight away you can get your oxygen. And make a note that it is better for basically as a way of enriching oxygen. You're not really making use of the nitrogen. Now, this is another where you're really doing it by solubility. So it could be something like you're mentioning about pyrogalol. Okay, but the commercial unit which is there actually makes use of molten salts. So you take a eutectic of some maybe sodium nitrate, sodium nitrite, that kind of a salt mixture which can form a lower melting eutectic. And what has been found is that at a particular temperature, like let's say something like 900 to 1200 degree Fahrenheit, that oxygen has got high solubility in this molten salt. And then what you do is that you take it from this particular bed into, which is known as an absorber, because you're absorbing the oxygen, and then you take it to a desorption unit, and where you have to heat it up to higher temperatures, and at those higher temperatures, again the oxygen loses its affinity for the molten salt, and you can take out the oxygen. Okay, so this is the desorber and this is the absorber, and then after the oxygen has been removed, then you put it back into this particular unit. Now, all of these go through the very similar, the pre-treatment part is very similar. So you may actually get rid of CO2, H2O, etc. with the help of molecular sieves, and make sure that only pure air is going into the system. And just like we had learnt in the contact process, all of these things are made practical basically because of the heat exchange that takes place. So, for example, when I'm absorbing my oxygen, 4/5 of the air, which is nitrogen, is coming out hot. So I've got a hot nitrogen coming out from here. And then when I'm doing desorbing, and I've got pure oxygen coming out from here. So I've got again pure hot oxygen coming out from here. So what I do is that I heat up my incoming stream, this one, and cool these streams by heat exchange. So that's really what you're doing. So from this one, you can see that you get oxygen out, and you can compress that oxygen. You can make oxygen cylinders out of it, and it's high purity, 99.9%. So nitrogen has no affinity for this. Only the oxygen has affinity for the molten salt. From this, whatever nitrogen came out, that's your nitrogen. Many times, the purity of the nitrogen is also quite good, and you might be able to make use of that nitrogen. But usually there will be some amount of oxygen which will be present. So the nitrogen may be treated more as a waste, rather than as a useful product. But this is in sum and substance the sort of thing that you do based on solubility. So now you can of course look at various other things like nothing like it that if you could absorb a lot of oxygen into at maybe room temperature, then naturally it will be a more attractive process. So one could look at the things like, for example, there are some fluorinated molecules which have got very high affinity for oxygen. Like for example, in blood, I mean, some of the artificial plasma, etc., which people are looking at, which are fluorinated compounds, they've got the ability to dissolve a lot of oxygen. There would be considerable room for variants, and that's where your knowledge of chemistry would be useful. That what kind of things can dissolve oxygen selectively. And remember, this is absorption, whereas the previous one was adsorption. Problem with this unit is really one of corrosion, because you're having molten salts at a fairly high temperature. And so under those conditions, naturally, corrosion can be a problem. So you require special vessels for this. By the way, I must also tell you that these molten salts are also being used as a means of storing solar thermal energy. So you can actually have parabolic dish kind of concentrators, which reach very high temperatures. It melts the salts, and then you can heat them up to high temperatures, making use of the solar thermal energy. And then at night, you might be able to extract that heat and run a turbine and generate power. So these molten salts are extremely useful and today being actively looked at. But I hope you can also see the very diverse nature of the applications of some of these compounds. Now this one is based on the size difference. So these are membrane modules. It could be a hollow fiber membrane, or it could be a flat sheet membrane. And what it does is that these membranes have a certain porosity, and because oxygen molecule has a marginally smaller size, you can see 2.96 angstrom spherical radius, effective spherical radius, and nitrogen is about 3.16 angstrom. So that actually translates to about 3 to 4 times higher permeability of oxygen through these membranes. So I can actually therefore permeate oxygen selectively, and you might be able to reach maybe purities of around say 50, 60, 70% of oxygen, which is not bad. And especially because this is a very low cost unit, very affordable unit. And so if you, for example, want to do more efficient combustion with enriched air, I mean not 100% pure oxygen, this is an ideal unit. Or even for many of the, I remember I was talking to a doctor for Engg, and I was telling him that we should make some affordable units, and this would have been about 2 years back, and he told me, yeah, anything which is more than 20% oxygen, even if you get 30%, 40%, 50%, that's not bad. Maybe for rural areas, etc., it could be an ideal technology to apply. Right? So, and the rest of it, of course, the filter and all those things are all constant. Now, this one takes advantage of the greater ionizability of O2 compared to N2. It's really because, as we discussed, you have got unpaired electrons in the antibonding orbital, and so obviously it's easy to kick off at least one of these electrons and to form O2 plus. But this is not something that happens at low temperatures. Typically, you require high temperature, something like maybe 1100 degree Fahrenheit, to pull up the electron. Now, what actually it does is that you have these modules. These are actually ceramic membranes. You have to use ceramic membranes because polymeric membranes would obviously not withstand these kinds of temperatures, whereas ceramic membranes will. So you have got ceramic membranes, and these ceramic membranes are ion transport membranes. So applying an electric field across these membranes under those temperatures and in the presence of the electric field, the O2 becomes O2 plus, and then the O2 plus permeates on this side because of the electric field. And of course, your electron, which you lost at this point, that electron can flow into the other side. And so at the permeate end, your O2 plus can again become O2. And so you've got pure oxygen, And then exactly like in the previous case, you take advantage of heat exchange method to make the process energy efficient. And so whatever oxygen you're getting out, this oxygen, that's your oxygen. And the reject stream from here, which did not pass through, which is basically predominantly nitrogen, all the reject streams you collect, and that will be your nitrogen. Okay? This is based on the fact that you have generated O2 plus. Okay? So you have seen it's very different. One case O2 plus, another case you are taking advantage of the size difference. In another case you are taking advantage of the quadrupolar moments being different, and in another case you saw the solubilities of these oxygen and nitrogen are different in molten salts. So you can see very different ways of doing this. There are also people, let me tell you, who have been looking at sweeping out that oxygen which you get here with something like, say, natural gas, methane. So then natural gas and oxygen, you can react, and so you'll form syngas. Now, why would you do this? Because you have to obviously generate the syngas, etc., at high pressure. And if you had a huge amount of nitrogen, obviously the partial pressure of nitrogen would be high. What it means is that you would have to pressurize these things to a much higher levels to achieve the required partial pressures of oxygen and natural gas. So naturally, getting rid of the nitrogen helps you to have a more reasonable kind of a pressure for converting it into syngas. So those are the reasons why you would want to get rid of the nitrogen in this particular case. In fact, when I was looking at all of those methods, I realized that there is a very fundamental process that is used today, which is not even covered in those approaches. I was just looking up this Alibaba site. This unit, for example, you can see water electrolysis. It costs about maybe $1,000 to $3,000. Okay, and it gives you extremely pure oxygen, 99.999% oxygen. They didn't say actually what was the mechanism by which they get pure oxygen, but from whatever I could make out of from the description of the unit, I thought I'll try to write it down in terms of half cell reactions that take place, and I believe that this is what happens. I'm not 100% sure, but I think I'm okay. I was right probably. Now, so what you're doing, it's quite interesting. You take air at the cathode. The cathode, of course, you are reducing the oxygen in the air, not the nitrogen. Obviously, nothing happens to the nitrogen. It's not reactive. So I believe that the reaction that is happening is O2 plus 2H2O plus 4 electrons coming from the anode, and you make 4 OH minus. So you're feeding in water. So that's the water, and you're pumping in air, and the oxygen is reacting, and you're forming 4 OH minus, and the rest of the air stream, which is basically the nitrogen, it's flushed out. It just goes off, and then you continuously keep pumping more and more air. Now, what happens is that this particular polymer, it's a polymer electrolyte. What it does is that it maintains ionic conductivity. So what happens is that the hydroxyl ions which you're forming here, okay, those hydroxyl ions travel from the cathode to the anode. It travels because there is an electric field gradient. So that actually helps the OH minus to migrate, the OH minus which is forming, to migrate towards the anode. And in the anode, what happens is basically you are just doing the oxidation reaction. 4 OH minus will become oxygen and water. And this electron, the 4 electrons will basically flow here, and you'll continue the process. So effectively, what did you do in this process? What did you do ultimately? See, all you did was that you took in air, but you excluded the nitrogen because it didn't react. Only the oxygen reacted and formed OH minus. These membranes are such that they don't allow the nitrogen gas to pass through on this side. They only allow the ion transport and blocks of the nitrogen. So on this side, now I don't have nitrogen. I've only generated pure oxygen. So effectively, what I did was I excluded nitrogen. That's all I did. But I did it in a very clever way of carrying out the reaction and the reverse of the same reaction at the cathode and the anode.
Sir, I have a doubt regarding this, sir.
Yeah.
So, don't we have to like add a little bit of acid to the water?
Wonderful question. See, what happens is, this is a very good question you've asked. What happens is that this polymer electrolyte system itself is like your solution. It has been designed in a way that your water and your air is actually going into the like somewhere here, and then the OH minus. I mean, obviously, the construction of this polymer electrolyte membrane is a bit complex. It's not as simple as the way I've shown you. So that you can actually do electrolysis with pure water because the ionic conductivity is being sustained by the membrane. So you don't really need to put acid and things like that. And now I'm not very sure whether they do have an acid or not. Something tells me that you don't need it, and it can be done by the polymer electrolyte membrane. And that's why it's called polymer electrolyte. In other words, it's also serving the purpose of the electrolyte. You understood?
Yes, sir. Thank you, sir.
We've looked at various methods. See, all of these are good for small units or things where you don't need very high purity of oxygen and nitrogen. And even if you get, you'll get one of those pure and the other one impure. Now what we'll discuss is how to get both oxygen and nitrogen in a pure form. And we will look at how the boiling point differences have been exploited. Suppose I take air or oxygen and I cool it down and I have a certain pressure and temperature and moles of gas, I know that the equation is the ideal gas equation is PV is equal to nRT. But we also know that gases like oxygen and nitrogen are not ideal gases. Okay, they're non-ideal, and they're non-ideal because there is attraction among the molecules of the gas, and also that they have a finite size. And so, for example, if I try to increase the pressure beyond their intermolecular distance, then obviously things like the Lennard-Jones potential will become important, and there will be a massive rise in the energy of the system. So those are the two terms, the A term and the B term. The B term is the size term which I have to take into account. This size is a small size, a very negligible thing when the volume is large. But as I reduce the volume of my container and make it very, very small, which means that suppose I pressurize the system such that I reduce the volume to very small volumes, then of course this factor will become important. Suppose I've got a gas where there is 2 moles of oxygen and I've got 30 liter of my volume of the flask, and let's say my temperature is 298 K, 25 degrees C. Can you calculate the pressures considering the ideal gas, that is PV is equal to nRT, and in the case where I'm actually putting in the equation for the non-ideal gas, and the A and the B terms have these values 1.378 liter square atmosphere per mole squared, and B is equal to 0.03183 liter per mole. These values are a bit different from the values which I've shown here, but don't worry about it. Can you quickly do the calculation and see if for the ideal gas you get this pressure, and for the non-ideal situation that you get this pressure, and for R you can take 0.08206, and for T you can take 298.15 K. N is given to
Yes, sir, the values are correct.
correct. Okay. And so what you can see is that when you are under ambient conditions, the A and the B terms do not really make a very significant effect on the pressures, and these two pressures are virtually identical. Now consider a situation where let's say I have reduced the volume to from 30 liter to 0.5 liter, okay, and I've reduced my temperature from 298.15 K to 150 K. See if you are getting these two values.
Yes, sir. Similar values.
Yes, sir.
Similar values. Great. So what you can see is that as I'm reducing the volume, obviously if I have an ideal gas, I know that how P will vary with V and P will vary with T. But what you're now seeing is a substantial deviation from the ideal value. And the real pressure is considerably lower. Can someone tell me why is this pressure so much lower in this particular case?
So in the ideal case, we don't consider the interaction between gas molecules.
Brilliant. So what happens is you can see for yourself, and that's why I wanted you to do the calculation, that you see, when we talk about pressure, it is the rate of collisions that you're having with your vessel, the walls of the vessel. As you are reducing the volume, the molecules now are interacting with each other, and so the number of collisions with the wall is going down, and you have got it's substituted with more interactions between themselves. So effectively, this is the reason for the deviation. Now, obviously, under these conditions of volume, we still haven't come anywhere near the situation where repulsive interactions would be high because of the size of the oxygen molecules. That size component is still only a tiny fraction of the total volume of my vessel. So effectively what you have is really the effect of the attraction term. The attraction is the one which is leading to reduced number of collisions with the wall. So we will just go through this now and stop. Now this is really your pressure volume isotherms. So these are taken for different temperatures, and we know that for an ideal gas, if your pressure goes up, your volume will come down. If your volume goes up, your pressure will go down. That's what you have. Now, as you're reducing the temperature, it's more or less behaving the same way, but you come to a point like here where you can see an inflection. This really is your critical point where there is some amount of liquid formation in your gas because of this non-ideal behavior. Effectively, the critical point is one where you're not able to distinguish between the liquid and the vapor state, but they're there. Their densities are comparable, they're same. As I go to lower and lower temperatures, now what happens is that I've gone into the place where this side, this line, the right of the blue line, this one is of course all vapor, my gas state. Okay? The left of the blue line, this one, is all liquid. Okay? And this is the place where liquid and vapor coexist. So you can think of this part as if it is a superheated liquid and this part as a supercooled vapor. But basically this is the range where you have got both liquid and vapor which are in equilibrium, and over here it is all vapor and here it is all liquid. You also can figure out that this part is really what I will call as the point G. I'll call it as the dew point because that's where the liquefaction is taking place. You can read this part in more detail, and we will continue from here in the next class, okay, tomorrow. But please have a look at this curve in more detail and just make sure that you understand it. Any questions from anyone? All clear?
Yes, sir.
Okay.
Thank you, sir.
Thank you.